Welcome to today's video. Today we're going to solve the 1 plus 1 dimensional wave equation. The wave equation is a fundamental equation in physics, describes oscillatory phenomena and propagation of waves. And the particular example that we're going to see here is the 1 plus 1 decays that models a string attached to whatever, about the vibration of a string in any configuration. Now, the particular case we're going to solve is we're going to attach the extremes of the string to two firm posts. I think of a guitar or a piano, whatever. So you have strings that are tied to something at the end, so the ends don't move because they're tied to something. So you see, for all times, this doesn't move. U is the amplitude as a function of time and space. So the extremes don't move, and those are the boundary conditions. And the difference with the heat equation is that this equation is a second order equation in time as well, not first order. So we need two initial conditions that physically make sense because we need to specify the shape of the string at the beginning. How do I start? So I hold it like that or whatever, what is the shape, but also the momentum that we give it when we play the guitar, the momentum that we give it, the velocity profile, the time derivative of the amplitude, okay? So the initial conditions are two, and it's one on the amplitude and one on the derivative of the amplitude, typically. And the boundary conditions are two, typically also what happens at the extremes. Okay, in this case, that they remain tied. So these are called actually Dirichlet boundary conditions. All right. So we solve this equation the same way that we solve the heat equation. We make the answer that the equation is separable. So we assume that the equation, we ask math if the solution is of the form t times x, where t is a function of only t, x a function of only x. So we repeat the same procedure as we did before, and we plug in this into this equation of what we get. So the left-hand side will give me t dot dot t x of x, right? I take the derivative with respect to time, and the right-hand side is c squared t of t x dot dot of x. Now you remember the next step was let's write everything that is only a function of t on one side of the equation and everything that's a function of x on the other side of the equation. So we write t dot dot divided by t, right? Putting this here and then putting this here, it's equal to c squared x dot dot of x divided by x. All right, wonderful. So what we do now is same as before. We come to the realization that this is a function of only time. This is a function of only x. So because this is a function of only time, it cannot depend on x, but this side cannot depend on t. So if this has to be true for all values of t and x, the only possible way is that neither of these two terms depend on neither x or t. Because if this depends on t, then it will be equal to that cannot depend on t. And same, if this depends on x, it cannot be equal to that cannot depend on x. So both sides have to be constant, and we call that a separation constant lambda. Now, in the previous case, we call it lambda. It's a separation constant. I can call it Joshua if I want. Here it's more convenient to call it minus lambda than lambda. I mean, you can call it lambda and so there's no problem. It's just more convenient in the sense that we're creatures of habit, and if we want something really similar to the previous case, we're to call it minus lambda. And the reason is that unlike the heat equation, if you remember, in the heat equation, when both were on the same side of the equality, you have a plus sign, here you have a minus sign. Time and space enter with different signature. And that, if you really want to reproduce the pattern that we had in the previous exercise, better call this minus lambda, and then everything will be fine. It's an arbitrary, let me just call it minus lambda for this exercise, all right? Now, but that means I have two equations, right? And the two equations I have is, let's write, first equation I get is t dot dot divided by t, right, equals minus lambda. So what does that mean? Well, what that means is that the equation for t is t dot dot t plus lambda t of t equals 0. Second order linearity of constant coefficients, easy peasy. We can write here the characteristic equation, L squared. Let me call L the eigenvalue, the variable of the characteristic polynomial. So L squared plus lambda equals 0. Okay, that's the characteristic equation. all right, to find the roots of the characteristic polynomial that is L squared plus lambda. And what do we have in this side? On this side, we have, if we write it, well, let's write it like that, x dot dot, x, it's equal to minus lambda c squared. Okay? Let's put the c squared there. So what does that mean? Well, that means that I get the equation x dot dot of x plus lambda divided by c squared x of x equals 0. So in this case, the characteristic equation would be m squared plus lambda divided by c squared times nothing equals 0. That's to find the roots of the characteristic polynomial. And now we know how to solve these equations. Those are second order linear ODEs of constant coefficients. Depending on the value of lambda, I got three possibilities. Either a sum of exponentials or sinus or cosines, which is the same as we saw in the previous video, or at trigonometric, sum of trigonometric functions, sine or cosine, or we can have that lambda is 0, in which case it typically was an exponential times a polynomial, but because in this case the exponential is times the eigenvalue that is the double root, and this case is 0, not times exponential of the eigenvalue times the variable, then we get that it's just a first order polynomial in that case, same as we saw for the heat equation. Let's consider the different cases separately, right, before getting to solving the equation. You see, this is going to be very, very similar to what we did with the heat equation. Because the boundary conditions are very similar, we're going to impose the same kind of boundary conditions. The only difference is that the equation is second order in time as well. Things will change a bit when we impose the initial conditions, because now we have two, so it'll be slightly different than before. Not much, just slightly. All right, so let's get to it. Different cases. Case number 1. Lambda equals 0. All right, when lambda is equal to 0, then we know that the solutions, let's take like this. So let's call, we have this is m squared equals 0. So it's very easy, x of x. In this case, well, let me write it like that. It means that m equals 0, double root, but also L equals 0, double. As you can see from this equation, solve for L and for m. And that means that x of x would be bx plus a, and t of t would be c t plus d. All right, so we don't need all those constants. We can suppress one of them because it's a product of the two, but I wrote all of them for clarity now here. All right, so let's check case 2. Case 2 is lambda larger than 0, and that means in our case, in this case, let's call it lambda is equal to omega squared, okay? And then that means that m, which is equal, of course, to the square root of lambda over c squared, in this case is equal to plus minus the square root, okay, two roots. So this is equal then to plus minus omega over c. All right? So there are two real roots, and that means that the solutions are of the form x of x is equal to a e to the omega over c, that's the eigenvalue, x plus b e to the minus omega over c x. All right, wonderful. We learned in the previous lecture that equivalently we can write this as some different constant, but again, arbitrary constant anyway, so I could even call it a, but just for clarity, I call it a tilde. This is cosh omega over c x plus b sinh omega over c x. Now, what is the c that is appearing here, this constant? Well, if you check dimensions of this constant, it has dimensions of speed. C is the speed of sound, it's the speed of propagation of the waves, okay, as we will see. All right, wonderful. And what happens with t in that case? Well, L is equal, in this case, as we have there, right? Right. So L is equal to plus minus lambda, right? Square root of lambda so that's omega. So the solution in this case for t is t of t equals, same as before, let's call it c e to the omega t plus d e to the minus omega t. Now again, we don't need all those constants because they're going to be multiplied, okay? So it will be enough with 3 of them, but nevertheless, we write all of them for now. And then this is the same as c tilde, if you want, sinh or cosh of omega t plus d tilde sinh of omega t. We can use either or. I mean, if you like the exponentials or the coshes, it's the same. Whatever is most convenient for your exercise. Right, let's see case 3. Case 3 is lambda less than 0. And same as before, what we do, we call lambda minus omega squared, because we know that it's negative, the square of a negative real number is positive. So, in that case, we know that m is equal to plus minus the square root of lambda divided by c squared, which is equal to plus minus I omega over c, two complex conjugate roots with no real factor in front, with no real part. And that means, and L, I'm going to write L here, L is equal to plus minus square root of lambda, which is plus minus I omega. So we get that x of x is equal to A, the oscillatory functions, right? Cosine of omega over cx plus B sine omega over cx. Actually, note that I'm doing that, I can also do it, if I wanted, I could do this as well. A tilde would be e to the I omega over cx plus b tilde e to the minus I omega over cx, which is the same as doing exponential functions to hyperbolic sine and cosine, trigonometric, usual circular cosine and sine. In terms of complex exponential, same thing. Okay, we could do either or at our convenience. And for t, I'm not going to write it like that for t, but I could if I wanted. For t in this case, we would have a c cosine of omega t plus d sine omega t. Alright, so those are the three cases that we have in this case. Let's collect what the results are like in the three cases, put them somewhere there, and let's start to solve the problem at hand. Alright, let's do that. I moved and summarized the solutions here. I didn't write this in terms of complex exponential because I'm not gonna use that at all. This I wrote because it's more common for the particular case that the lambda is greater than 0 to use the hyperbolic versions because are easy to impose boundary conditions on. And let's proceed now and let's find the solution to this problem. The problem that we have is I give you some profile of amplitude, I give you some profile of velocities for the string. I tie the string to two extremes like in a guitar, and I want to know how the string is going to vibrate in time, how it's going to behave. Alright, so let's begin with case 1. Let's see if there are any solutions on case 1. Case 1, we know that u of tx is equal to x of x times t of t. Alright, wonderful. So let's start imposing the boundary conditions. So the first thing we always do is the boundary conditions. And the boundary conditions here tell me that u of t0 equals 0 and u of tl, which is the length of the string, equals 0. Let's do this one first. Alright, so that means, again, I can have here, this thing is on the, I'm going to just write it here once, this is x of x times x of 0, sorry, times t of t, and this equals 0 for all values of t. So I can divide that, and what this is imposing is that x of 0 is equal to 0, okay? Alright, so that means that x of 0 is equal to 0. That gives me, I take x from here, b times 0 plus a equals to 0, which means a is equal to 0. Alright, what does the other condition give me? Well, x at L is equal to 0, tells me that b times L plus a is equal to 0. But now I can use that A is equal to 0, and that tells me that B times L is equal to 0. Two possibilities: either L is equal to 0, which is incompatible with a string of a finite length, and the other one is that B is equal to 0. So all the options that we have tells me that this is the 1 and the 1. So in this case, we get the trivial solution. And the trivial solution, there is nothing happened, the string is stationary and doesn't move at all. It's not compatible with an initial condition that has some movement or some shape. So in this case, it's incompatible with the initial conditions. All right, so no solutions that are valid in our case from case 1. Wonderful. Let's check case 2. So case 2 is similar to the previous one. So we impose, let me just write here that what we're imposing here is the boundary conditions. Always impose the boundary conditions first. And in this case, what changes is the form. Let's take the hyperbolic ones, because it's usually simpler to play with those. So we get in this case that A, let me skip the tilde for convention, of the cosh of 0 plus B tilde, the sinh of 0, it's equal to 0. Now the sinh of 0 is 0 and the cosh of 0 is 1. So that tells me that A tilde is equal to 0. All right. What does this one tell me? This one tells me that A tilde of the cosh of omega over C times L plus B sinh B tilde sinh omega over C times L equals 0. But I can use that A is 0, so what this means is that B times the sinh of omega CL is equal to 0. All right, several options here. Well, divided into families if you want. First, either B tilde is 0 or the sinh of omega over CL is 0. This one implies the only 0 of the sinh is when the argument is 0. This one would imply the omega over C times L is equal to 0. What are the options here? L is 0, inconsistent. And the other ones, C, omega over C is 0, which is inconsistent as well, because we're in the case that omega, I didn't write it here, but case 2, yeah, lambda is omega squared and lambda is valid as 0, okay? And C is a positive constant. So yeah, indeed, these two cases are not allowed. The only valid case here is this one, and gives me the trivial solution, which means that the amplitude of the string will be 0 always and everywhere, and it's incompatible with the initial conditions, incompatible with initial conditions where something happens, where you moved it, or it's in a different shape. Wonderful, so case 2 gives me nothing. Let's check case 3. In case 3, we're in that case over there. So the conditions that we have, the first one tells me that x of 0 is equal to 0, tells me that A cosine of 0 plus B sine of 0, it's equal to 0. I know the sine of 0 is 0 and the cos of 0 is 1. And that means that what this is telling me is that A is equal to 0. Wonderful. All right, now, so if I impose this one, I get A cosine of omega over C L plus B sine of omega over CL is equal to 0. But then I know that A is equal to 0, and that means that B times sine omega over CL is equal to 0. Several options. Could be that B is equal to 0, but that gives me the trivial solution, which is incompatible with any non-trivial initial conditions. The other option is that the sine of omega over CL is equal to 0. And that gives me an infinite number of solutions. Remember, that allows me to compute the eigenvalues, the omegas here. And that means that this means that omega, any values of omega for which omega over C times L equals n pi will cancel the sign. Wonderful, so that gives me an infinite number of omegas. Let's call them omega n. And these omega n's are n pi c divided by L. So when omega is n pi c divided by L, the sign of 0 and gives me an infinite number of solutions. We can write the infinite number of solutions. Let's write them as follows. So we will have that the x sub n, because there's an infinite number of them for n. I didn't write it here, but n is an integer. So xn of x is the constant, one different constant per case, so bn sine omega n over c times x, where omega n is each of these solutions. I can substitute, right? If I substitute, I get bn sine of the omega is n pi c over l. So I get the c cancels the c, and I get n pi over l x. Now let's compute what the t n's would be. T n's of t are, well, I go out to the solution in this case, and that tells me that the t of t would be, I have Cn in principle, a Cn cosine of omega n t plus dn sine of omega n t. All right, but now a little bit of thinking to optimize things. So the solution, the total solution, would be the product of the two, right? So we would have that u of tx is equal sub n. Each of the infinitely many solutions would be equal to the product of the two, right? xn of x times tn of t. Now we can optimize this quite a bit, because we realize that we have an arbitrary constant multiplying to arbitrary constants. Oh, this constant is irrelevant. I can reabsorb the bn into the cn and dn. So I can write this product as follows. That should be, let's write like that, cn cosine of omega n. Let's substitute the omega n. N pi c l t. All right, times the sine of m pi lx plus dn sine of n pi c over lt times the sine of n pi lx. And what did I do? Well, I multiplied these two, and the bn I reabsorbed into the definition of cn and dn. Or if you want to define new constants with tildes, and reabsorbed the bn into the cn, and cn is the product bn times cn. That's nothing, it's an arbitrary constant, so just reabsorbed into these two arbitrary constants. All right, so I know that the solution has to be the sum of the infinitely many solutions that we have. So the general solution that satisfies the boundary conditions would be u of tx, the sum of all the un's, so it's sum n equals 1 to infinity of cn cosine of n pi c divided by lt times sine n pi divided by lx plus sum n equals 1 to infinity dn sine of n pi c divided by lt times sine n pi l times x. All right, so it's good that we are right here. This is certainly not the solution to the problem, but it's the solution of the wave equation that satisfies these boundary conditions. We have not touched yet the initial conditions, and that's the next step. We need to find the coefficients dn and cn that satisfy the initial conditions that we have here. All right, and that's going to be in terms of Fourier series, of course. Let's do it. All right, so we wrote the arbitrary constants like that, as before, the general solution as this sums like that in terms of the constants that we need to determine cn and dn. And I also need the derivative. And if I need the derivative, I have to take the derivative with respect to t, because remember, I have two initial conditions, one on u, one on the derivative on u with respect to t. And substituting doing the derivative gives me this. So right, as the derivative of the cosine is the minus sign, so that's the minus, and then the argument that multiplies t. Derivative of the sign is the cosine. Let's impose the initial conditions. And what do the initial condition tell us? So the first initial condition is u of 0x equals f of x. What does that mean? Well, let's substitute u of 0x from here. We see that when t is 0, this becomes a 1, and this becomes a 0. So there's only Cn terms, and they are on the left-hand side, becomes n equals 1 to infinity. Cn, cosine of 1, sine of n pi over Lx equals f of x. All right? And this means clearly that that allows me to determine the coefficients Cn. What are they? Well, clearly they are the coefficients of the sine Fourier series of f of x that is obtained with the odd extension of f of x that I have defined here. F of x is a function of x, that is this one, to 2L. So that's clear. The coefficients Cn's are the coefficients of the sine Fourier series of f of x. So we need to take the f of x that is defined from 0 to L, do the odd extension, right, to get the sine Fourier series, so the period for the odd extension. Remember, the period is 2L for the odd extension, and then we get that the coefficients are, well, let's do the whole thing, 2 over the period over 2L integral minus L. Let's call capital F the odd extension of x, okay, times the sine of n pi Lx. Wonderful. But then what we get, because that's the procedure to find the Fourier sine series. Remember, if you don't remember, please go back to how to obtain the half-range expansions, in particular the one that is the sine series, which is associated with the odd extension of the function f. All right, but then I know, so this cancels, but then I know that this is odd because it's the odd extension, and this is odd, so the whole thing is even, so I can write that as 2 over L, the 2 being from doing the following, 0 to L, dx, small f of x now, because it's in the half, that is f of x from here to here, from 0 to L, sine of n pi Lx. And that is, I didn't write it here, those are the coefficients Cn, okay? So this is the solution. Well, of course, if I give you a function, you have to do these integrals, or it could be that you can do it by inspection, as we did before. That is an easy Fourier series to do. At the end of the exercise, we're gonna practice some by inspection to see how you get them, but it's the easiest way when it's by inspection. But you can always do this integral and find it. Now, how do you find, let's find, so that determines the Cn's, but we don't know about the dn's yet. How to determine with the dn's? Well, with the other initial condition. The other initial condition tells me that the derivative with respect to t of u at 0x is some function g of x. So if we go here, we see in the derivative with respect to t that when t is 0, the sign cancels and the cosine becomes 1. So this is on the left hand side, n equals 1 to infinity, and we get dn times n pi c divided by L sine n pi divided by L equals g of x. Now, we cannot say now that the dn are like here. So let's look at here. Here, the Cn's are clearly, you can identify them as the coefficients of the sine Fourier series of f of x from 0 to L. Or what is the same, and these are important things, so remember them. What is the same? That Cn's are the coefficients of the Fourier series of the odd extension of small f of x, which is what I call capital F of x, okay? And that's why I found this formula for Cn. In this case, it's not as simple, because we will need to have something like this, n equals 1 to infinity, let's call it small dn, sine of n pi L equals g of x. Now, if this were like that, then we would know that the small dn's would be certainly the coefficients of, let's write it like that, 2 over L integral 0 to L of the odd extension, the Fourier series of the odd extension of g of x, right? So it would be like that, sine n pi over L. But the small dn's, not the big dn's. Well, but that's easy, because to identify the two, we just realize that we can define dn, small dn, as capital Dn, n pi c over L, and then it looks like that. So one more step, dn, it's equal to, I substitute this, well, I can maybe, this is equal to substituting the dn, so dn times n pi c divided by L. We can take this and put it on the other side and we get the dn's. So dn is equal to, the L cancels, alright, so I'm going to get 2 divided by n pi c, and then the integral 0 to L dx gx sine of n pi over L. And that's it. Those are the coefficients, the n. Now that gives me the solution. Let's write the solution. Let's just recap. Let's write the solution here, substituting the values of dn and cn. So it's a long-ish solution, but let's do it. There you go. So this is what you get substituting the cn's and the dn's, and that would be the solution. So now to compute these coefficients, right? You have two options. Either this function for you. Either this function is easy and you know how to compute the Fourier transform because we've done it in class. For example, we've done many Fourier transforms in class, so one of those. Or because maybe you can see it by inspection. For example, in the simple case, like imagine that f of x in this case was, because it was given there, I don't know, 8 sine of 9 pi divided by Lx plus 1 over 2 sine I don't know, 13 pi divided by Lx, right? Plus, I don't know, 9 sine of 42 pi divided by Lx. Now, in this case, we know exactly what the Fourier series would be. We know the cn's, because again, the cn's are the coefficients of the f, of the sine series of the f. This is a sine series. So we know then that the cn's are C9 is 8, C13 is 1 over 2, C42 is 9, and then all the others, Cn, different from 8, 13, or 9, they're all 0. Alright, so we only have 3 summands in here. I could have given you something for the g of x as well. So imagine that the g of x were, okay, the g of x is slightly more complicated. Let's say, imagine that we have, let's give 3 sine of 3 pi divided by Lx. So imagine that were the g of x. So we know, in this case, that small d, remember the coefficients here are the small d, not the capital D, and there was this relation of small d, right? It was equal to n pi c divided by L, capital D, if you remember, all right? Because of this. So the dn here, we know that the d3, it's equal to 3, and all the dn's different from 3 are 0. All right, cool. So that means, this is the dn, right? So that means that from that, we know that the dn's, right, are equal to dn now multiplied by L divided by n pi c. So in this case, we know that d3 is equal to L divided by 3 pi c times dn, which is 3. So in this case, the L and d3 would be just L divided by pi c. Okay? So if we now imagine that I want to write the solution, assuming that f of x was given by that and g of x was given by this one, then the solution would be, now substituting not in here, because that already has the integral, substituting in here at this level, then we just get the substitution of the c of n. So we have three summands for the first sum. So the first one is C9, so which is 8. So I get 8 cosine of 9 pi c over LT times the sine of 9 pi Lx. All right, wonderful. And then that's the first summand. The second summand would be with C13, and it's a 1/2 factor. 1/2 cosine 13 pi c divided by LT times the sine of 13 pi L times x. All right, let me write next one here, plus now the 42 one, which is 9 times cosine 42 pi c divided by LT. This is a c, all right, times the sine of 42 pi c divided by L, 42 pi divided by L x. And then we have one summand on this series with the dn, and there's the d3, and the d3 is L divided by pi c. So that would be plus L divided by pi c, and then sine of 3 pi c divided by LT times the sine of 3 pi L times x. And that is the solution. That's the one that would correspond with this choice of f of x and this choice of g of x. All right, well, I hope that this wasn't too difficult. With this, we finished the lecture on the wave equation. There's one more equation to go, which is the Laplace equation, and we will be finished with the topics of the course. I'll see you in the next video. Bye-bye.